Hello students, today we will talk about conductometry, which is sometimes also known as conductometric titration. The outline of the lecture is we will talk about the basic points of conductometry, then Ohm's law, conductometric measurements, factors that affect conductivity, conductometric titrations, types of conductometric titration, and then advantages of conductometric titrations. There are few basic terms involved in conductometry, and therefore, we will discuss them in the brief in the beginning, like resistance, resistivity, conductance, specific conductance, molar conductance, equivalent conductance, and cell constant. The first term is resistance. The tendency of a material to stop the flow of current is known as resistance, or resistance is also called as a measure of the conductor's opposition to the flow of electric charge. R is defined as 1 by C, where unit of resistance is ohm. The second term which we use in conductometry is resistivity, which is defined as the resistance of a conductor of 1 centimeter length and an area of cross section equal to 1 centimeter square is defined as R is equal to rho L by A, where rho is resistivity of the material, A is the area of cross section, and L is length in centimeter. Therefore, we can write it as rho is equal to R A by L, where A is 1 centimeter square, length is equal to 1 centimeter. In such case, rho is equal to R. The unit of resistivity is ohm per centimeter. The third term involved is conductance. The reciprocal of the electrical resistance is known as conductance or electrical conductivity. Here we define it as C is equal to 1 by R, which means conductance is opposite to resistivity. When resistance is more, conductivity will be less. When resistance is less, conductivity will be more. A conducting solution obeys the Ohm's law, that is, the current flow through a conductor is directly proportional to the potential difference across its end. Here we can define it as I is equal to E by R. Remember, conductometry and conductometric titrations, they are usually used as synonyms. Conductance is directly proportional to the area of cross section and inversely proportional to the length of uniform conductor. We define it as C is equal to kappa A by L. This K is known as kappa. The units of conductance in SI unit we use Siemens, which is written as capital S, or we write it as mho, MHO, or ohm inverse. The word mho is coming by writing ohm in the reverse, and therefore we write it as M first, H in the middle and O in the end, and we use it as mho. So, in SI unit we use Siemens, whereas in CGS unit we write it in per ohm or normally written as mho. The Siemens is also the equivalent of an ampere per volt, which is A divided by V. Another term which we are going to use is specific conductance. The reciprocal of the resistivity is known as specific conductance. It is denoted by kappa k, which is equal to 1 by rho, which means we can also write it as kappa is equal to C multiplied by L by A. Again we can write it as 1 by R, because we know that conductivity is opposite of resistivity. Therefore, we are writing here kappa is equal to 1 by R into length divided by area. The units of specific conductance is per ohm per centimeter, or S, that is Siemens per centimeter. Another term which we are going to use today is molar conductance. The conductance of a solution containing 1 mole of a dissolved substance when placed between two parallel electrodes which are at unit distance apart. You can see here the distance between the two electrodes should be unity and have cross sectional area larger enough to accommodate the whole solution between them. It is used to study the current carrying capacity of an electrolyte at different concentrations. We represent it in two ways: one lambda, which is also sometimes written as opposite V, and this is equal to kappa multiplied by 1000 divided by C, where C is in mole per centimeter cube and kappa in Siemens per centimeter. The unit of molar conductance are Siemens per centimeter square per mole, or sometimes we use it as Siemens per meter square per mole. Equivalent conductance is defined as the equivalent conductance of the solution as the conductivity of the solution containing 1 gram equivalent of the electrolyte when placed between two sufficiently larger electrodes kept at 1 centimeter apart. Here, as I told you, we are writing it as lambda equivalent or opposite V equivalent, which is equal to kappa multiplied by 1000 divided by C, where C is in gram equivalent per centimeter cube and kappa in Siemens per centimeter. The units of equivalent conductance are Siemens per centimeter square, gram per equivalent, or Siemens per meter square, gram per equivalent. In most of the books, the units which are followed or reported for conductivity is in CGS units. Therefore, let us compare the CGS units for various conductance. For molar conductance, the unit is per ohm centimeter raised to the power minus 2 per mole. For specific conductance, it is per ohm per centimeter, whereas for equivalent conductance, it is per ohm centimeter raised to the power minus 2 equivalent minus 1. Some factors that affect conductivity are size of ions, temperature, number of ions, charge of ions. Let us now come to the cell constant. The ratio of the distance between the two electrodes L to the cross section area A of the electrodes is called as cell constant. It is defined as K is equal to L by A, where K is cell constant, that is per centimeter. Remember, this K is different than kappa, which we are writing in a slightly different way. A is the effective area of the electrodes in centimeter square. L is the distance between the electrodes in centimeter. Let us consider the effect of various factors on conductance. The first one is effect of dilution. The conductance of a solution is due to the presence of ion. The degree of dissociation of electrolyte increases on dilution, which means more ions are produced in the solution. So, the conductance of a solution should increase on dilution. Let us now consider effect of dilution on the equivalent conductance. The equivalent conductance increases on dilution. The reason is the product of the specific conductance and the volume V of the solution containing 1 gram of equivalent of the electrolyte increases. Let us consider effect of dilution on molecular conductance. The molecular conductance increases on dilution. The Kharash law is the values of equivalent conductivity at infinite dilution for a large number of electrolytes were determined by the scientist Kharash, and it was observed that the difference between the equivalent conductivity at infinite dilution of the pair of salts having either a cation or anion in common is constant at constant temperature. For example, if we consider sodium bromide and sodium chloride as electrolyte and determine equivalent conductivity at infinite dilution, the values are 128.51, 126.45 and the difference is 2.06. If we now take potassium bromide in place of sodium bromide and potassium chloride in place of sodium chloride, the values are 151.92 and for KCl 149.86 and the difference is again 2.06. Similarly, if we now replace sodium or potassium by lithium, the values are 117.09, 115.03 and the difference is again 2.06. The equivalent conductivity of an electrolyte at infinite dilution is the sum of two values, one depending only on the cation and the other only on the anion. We can write it as lambda or opposite V equivalent is equal to lambda A plus lambda C. Weak electrolytes are not completely ionized even at high dilution. Hence, their equivalent conductivity cannot be determined. However, using Kharash law, we can determine it easily. For example, if we take acetic acid ionizes as acetate and H+. Therefore, the conductivity depends on acetate ions and hydrogen ions formed in the solution. However, the ionization of acetic acid is very little. The values of equivalent conductivity of acetate and hydrogen ions can be determined using some strong electrolytes. For example, if we take HCl, it will ionize as H plus and Cl minus. If we take sodium acetate, it will ionize as acetate ion and sodium ions, and NaCl would ionize as sodium ions and Cl ions. Now, if we add equation 2 and 3 and subtract equation 4, we can get the desired value, that is lambda acetic acid is equal to lambda acetate plus lambda H plus. Let us now come to conductivity measurement. The first part is electrode. Two parallel platinized platinum foil electrode or platinum black with electrode deposited porous platinum film, which increases the surface area of the electrodes and further reduces Faradaic polarization. The primary standard solution is required, which is usually KCl solution. Let us now come to conductivity measurement. We normally use Wheatstone bridge. The conductivity of the solution is determined on the principle of Wheatstone bridge. So, let us now consider this circuit. The first resistance is known resistance R1, the second known resistance R2, and here we have a variable resistance Rv and unknown resistance Ru. In the middle, we have a galvanometer for deflection and the current is passed through the Wheatstone bridge as shown in the circuit. Now, we have again shown this circuit here. We have a detector which is galvanometer. We have R1, R2, R3 and R4, and here we have a conductivity cell for which we are determining conductivity. So, that is, we are measuring resistance of a solution of electrolyte. Unknown resistance value, that is R2, can be determined, which will be equal to R1 multiplied by R4 divided by the value of R3. But this method has some difficulties when the direct current is passed through the solution. The first one, the concentration of the solution changes, the polarization sets in due to the substance liberated at electrodes. As a result, a back EMF is set up and resistance of the electrolyte is changed. These difficulties were avoided by the scientist Kharash as follows. He used an alternating current in place of direct current by increasing the surface area of the electrode, by using headphone and by using an oscillator. In instrument, the current source is the first one. He suggested that mechanical high frequency AC generator is need to be used, Weirland oscillator and vacuum tube oscillator. Here we must remember DC cannot be employed for conductance because electrode becomes polarized, leading to high cell resistance. This is a simple conductivity meter. Here you can see we have three important switches. The first one to cover the range of conductivity, second for the temperature, and the third one for adjusting it as on and off. The connection for the cell are provided in the back of this instrument. The conductivity cell is made up of Pyrex or quartz glass and are fitted with two platinum electrodes. You can see here we have two platinum electrodes which are fitted in a Pyrex or quartz glass and the solution is filled. Conductometry is a measurement of electrolytic conductivity to monitor the progress of chemical reactions. Or we can also say that it is defined as determination of measurement of the electrical conductance of an electrolyte solution by means of a conductometer. The instrument used for measurement of conductance is known as conductometer, and we have learned that unit of conductivity is mhos, that is per ohm, or Siemens per centimeter. Let us now consider Ohm's law. The magnitude of conductometric titration is based on Ohm's law. Here current I is equal to E by R, that is, the current flowing through the circuit depends upon potential and resistance. Here current is in amperes, that is I, E is the potential difference, and R is resistance in ohms. Let us now consider various factors that affect conductivity of the solution: temperature, nature of ions, the concentration of ions, the size of electrodes, and here we have a comparison for molar conductance of various ions at infinite dilution at 25 degree. You can see here for ions like potassium, sodium, lithium, H plus, silver, chloride, bromide and hydroxyl ions, the values are changing starting from 73.52 for potassium ions to 50.11, 38.69. For H plus, you can see here the value is largest because it is a very small ion. The value is 349.82. Again, it is 61.92 for silver and 76.34 for chloride, 78.4 for bromide and 198 for OH minus, that is hydroxide. The principle of the conductometric titration is based on the fact that during the titration one ion is replaced by another and invariably the two ions differ in their ionic conductivity, with the result that the conductivity of the solution varies during the course of titration. The equivalence point of the conductometric titration is determined by plotting the graph between change in conductance with function of the volume of the titrant added. The determination of end point of a titration by means of conductivity measurement is known as conductometric titration. There are various types of conductometric titration like acid base titration, precipitation titration, replacement titration, redox, that is oxidation reduction titration, complexometric titration. Let us consider few of such titrations. The first one is titration of a strong acid with a strong base, that is HCl with NaOH. HCl is a strong acid and NaOH is a strong base. In this case, the conductance of the solution is decreased with increase in added volume of NaOH due to the decrease in the free hydrogen ions. We have seen in the table that the conductivity of hydrogen ions is maximum because it is a small ion, and now when we are adding NaOH, these hydrogen ions are consumed and the conductivity is slowly decreasing. The formation of H2O takes place. After reaching the end point, the conductance is increased due to the excess of OH minus, which means now the curve will be, in the beginning you can see here we have a decrease of conductance, and at the equivalence point again it starts increasing because of increase in OH minus. Let us now consider titration of a strong acid with weak base, that is HCl with NH4OH. In this case, initially the conductance of the solution is higher and then it decreases due to the replacement of H plus ions. But after the end point, the conductance of the solution becomes constant as the ammonia cannot be ionized in the presence of ammonium chloride. Let us now come to titration of weak base with a strong base. That is, we are titrating now acetic acid with strong base NaOH, and titration of weak acid with weak base, that is acetic acid with NH4OH. Here you can see that initially the conductance increases, and then in the first case when we are using NaOH, the conductance after the equivalence point increases, as we have shown in the curve C here. But in the case D, that is when we are titrating weak acid with weak base, the conductance increases, but at the equivalence point it then again starts decreasing, as we have shown in curve D. Let us now come to precipitation titration. In these type of titrations, the ion is replaced by another ion having less rate of flow. This gives wide variation in conductivity. A reaction may be made on the basis of a conductometric precipitation titration, provided the reaction product is Sprengli soluble or is a stable complex. Here we can see that the conductivity in the beginning is constant, and at the equivalence point it starts increasing, because the reaction product is Sprengli soluble. Let us now consider a redox titration, that is titration of ferrous ions with dichromate ions. The basic reaction involved here is 6Fe2 plus is reacting with Cr2O7 2 minus plus 14H plus is giving 6Fe3 plus Cr3 plus and 7H2O, that is ferrous is changing to ferric. In this case, the conductivity is decreasing, and at the equivalence point the decrease becomes much lesser, and this point gives us a clear intersection point. Non-aqueous titrations can also be measured using conductometry. For example, titration of weak bases versus perchloric acid in dioxane formic acid medium. Titration of weak organic acids in methanol versus tetramethyl ammonium hydroxide in methanol benzene mixture. There are some advantages of conductometric titrations. The first one, there is no need of indicator, since change in conductance is measured by conductometer. We have seen that in a normal titration of NaOH with HCl, we use phenolphthalein as an indicator to monitor change in color. But here there is no need of indicator, because we are measuring conductance of the solution. Temperature is maintained constant throughout the titration. It is suitable for colored solutions where indicator does not show clear change in normal titration. Endpoint can be determined accurately, and errors are minimized as the endpoint is being determined graphically. There are several applications of conductometric titrations. In oil industries, it is used for base and acid number determination. This type of titration is used to check water pollution in lakes as well as in rivers. It is also used to check the alkalinity of the fresh water, and salinity of the sea water can also be checked by this method. To check the solubility of Sprengli soluble salts, this type of titration gives a sharp endpoint for the colored solutions. In summary, today we have learned the basic points of conductometry or conductometric titration, Ohm's law, conductometric measurements, factors affecting conductivity, conductometric titrations, types of conductometric titrations, advantages of conductometric titrations. With this, we come to an end of electroanalytical techniques, in which we have learned polarographic, voltammetric, amperometric, conductometric and potentiometric techniques. Thank you very much.